When watching the previous video, you may have thought to yourself that at some point in the future we might be able to exceed the speed of light by some means which we haven't yet discovered. But in this video, I'd like to address why the speed of light cannot be exceeded by normal means. To do so would mean that causality fails. To help us with this, I would like to introduce a graphical technique called a space-time or Minkowski diagram. In one spatial dimension, this consists of a simple graph with time on one axis and the spatial dimension, let's call it x, on the other axis. We could also fairly simply draw it in 2 dimensions as shown on the screen. However, although it exists in 3 dimensions, this would be almost impossible to draw, so I'll stick with either the 1 or 2 dimensional versions. Now we cannot stop time, it always proceeds onwards, so an object moving to the right at uniform speed would trace out a line on this diagram as shown. This is known as a world line of the object. In 2 dimensions, a whirl line of, say, a ball would look as shown on the screen. Lines of constant time, that is where things happen at the same time, on this diagram are horizontal. Such a line is called a simultaneity line. The x-axis is one such line at t equals 0. Similarly, a vertical line is the whirl line of a single point in space. Suppose we are standing at the origin of the graph at t equals 0, x equals 0, and we flash a light in every direction. We can draw on a diagram the path taken by the photons of light emitted. By convention, these travel at 45 degrees, so the speed of light is represented at 45 degrees on the diagram. The area of volume made by the beam of light like this is called the light cone. The light cone is important because since nothing can travel faster than light, this represents the area on a diagram that we can affect. Nothing outside this is within our reach. Let's see what happens if we observe another system moving at a different speed. Let's call this system 2. This would trace out a line on a diagram as shown. Because we don't know whether observer 1 or observer 2 is stationary, the whirl line for 2 is just as valid as the one for 1. And because of time dilation, its time axis is tilted as shown. To show you how these space-time diagrams can be useful, let's consider what happens if observer 2 emits a beam of light which reflects off a mirror back to the observer. From the point of view of us, observer 1, what happens is shown below. Observer 2 emits the light at point A, and from our perspective, 2 is travelling towards the mirror, and so the length alpha is longer than the length beta. However, from their perspective, observer 2's perspective, alpha and beta are the same distance because it considers itself not to be moving. The time at which it hits the mirror, labelled C on the diagram, is in between A and B for observer 2. The line joining C and the mirror is the line of simultaneity for 2, since it sees everything along this line as happening at the same time. This allows us to draw on the x-axis for observer 2, since this line is also simultaneous for t equals 0. On the diagram it's labelled x dash. Let's look now at 3 separate events which happen as shown on the diagram. From our point of view, from observer 1's point of view, A happens first. This is shortly followed by B, which happens some distance away, and then finally C occurs, which happens at the same place as A, but some time later. Let's now look at this from a point of view of observer 2. Things look rather different here. B now happens before A. This is because B is outside the light cone of A and C, as shown in the diagram. So A could affect or even cause event C, as a signal can travel from A to C. In fact, all observers will agree that A occurs before C for this reason. The fact that observer 1 and observer 2 disagree about the point B, one of them saying that it occurs after A and the other one saying that it occurs before A, is not really a problem because different observers observe things at different times. However, it becomes a problem if we allow a signal to travel faster than light. If a signal could travel faster than light between A and B, then observer 2 would see B causing event A. Time would appear to be running backwards, and causality would not be valid. So the ability to travel faster than light infers time travel into the past and a breakdown of cause and effect, something which we never observe in nature. And this leads us to the conclusion that travelling faster than light is not possible.